Okay, let me gradually get started. Probably supposed to do again today, when they come in. It is my pleasure to introduce Dr. Pawel Nadel-Turonski for the briefing talk today. I actually don't know him much. Actually, I know him for quite a few years. Pawel received his PhD in Sweden back in 2004. And after that, he spent a good 6 years at Jefferson Lab and studied all aspects of the nuclear structure of matter. I think since he spoke many projects, so that's his trait. And he's also a spokesperson in project. Our group has been heavily involved. Earlier part of Murad and now William is really building a detector for the next generations of Electron-Ion Collider experiment. Some of you probably follow the news. This project actually became the top priority of the nuclear science department. So that is the actual funding will start to flow in a couple of years. And so there are a lot of things we are making for, and as far as where the Electron-Ion Collider has been built, either at Jefferson Lab at Newport News, Virginia, or at Brookhaven National Lab in New York. And the Pawel actually played one of the major roles in Jefferson Lab, designed the ESA colliders for the Jefferson Lab, and also related to physics. And so now he is adjunct professor at Stony Brook University, also all the Canadian University. And I'm very happy to come in here to talk about the physics we love and enjoy. Okay.
Thank you very much for the nice introduction, and thank you very much for inviting me to give this colloquium. So this colloquium will be about the Electron-Ion Collider, as Chun mentioned, but the strong interaction, and the title comes from the particles which mediate this strong interaction, the gluons, which are the ones which bind everything together, as you will see. So this is a picture of the QCD vacuum, so it's not very empty. Maybe it's a good point to start. So before we move on to the Electron-Ion Collider, let me try to more broadly introduce the questions which we are trying to explore. You know that if we look generally at the universe, the current thinking is that most of it is dark matter and dark energy. And it will be very interesting to eventually find out what these are and which secrets are hiding from us there. But no matter how exciting, or maybe turns out to be fairly simple, this part is, the visible matter will always be very important to us, simply because, the visible matter is our universe. And we will always need to understand how that part works. And if we look at the visible matter, the colors here are a little bit off. I think you're used to that. So try to imagine the red as being a little bit more red. But so we have different layers in our world. If we look at what happens inside us, we have atoms with nuclei, and each nucleus contains protons and neutrons, which in turn are built up of smaller particles called quarks. And in the standard model, these quarks are sort of an elementary building block of matter. In addition to these matter particles, of which there are 3 generations, there are also the force carriers, which sort of bind everything together. But one very interesting point here is that if you look at the mass of a person or a microscopic object and look at the masses of these quarks, the mass of these quarks is about 1% of the mass of the object. So somewhere along this of structure, all the mass disappears, right? And in fact, in the early versions of the standard model, these light quarks here didn't have any mass. It turns out that you can describe everything very well without any mass associated with the quarks. Now, as it turns out, they do have mass. So this whole Higgs mechanism had to be introduced to explain why they do have these tiny masses. And although this is conceptually important, it doesn't matter so much at the end. And the mass that we experience instead comes from the interactions. And there are 4 forces in nature that we know of. Maybe there is a 5th one associated with the dark energy. But the ones which we know are the strong and the weak nuclear force, the electromagnetism, and gravity. Oh, thank you. The names can be a little bit misleading in terms of how strong they are. The gravity is truly the weak force, at least on microscopic scales. On large scales, gravity can be quite powerful. But in terms of interactions between particles, gravity tends to be very weak and neglected. But the strength of these different forces is a little bit more complicated than the name might imply, because the strength changes quite substantially with distance. So if we look at so this is okay. So let's look at this plot. So here on the vertical axis, you see essentially the strength of a particular force, and on the horizontal axis, you see the distance, or equivalently energy. So right, you go to short distances or high energies, and vice versa, going to the left, you go to low energies or large distances. So you can see that here we have electromagnetism, or the quantum electrodynamics. These little U1s, here, SU2s, SU3s, tells you something about the symmetry associated with each force. But if you look at here in this part, you see that when we go closer and closer to the center, so nearer the charge, the strength of the electromagnetic force increases. For the strong interaction, on the other hand, you see the opposite trend. So the strong interaction is very strong when you're far away, but it's as you move closer and closer, it becomes weaker. And there is this idea that maybe at some point all forces are of equal strength. Now, this is a hypothesis. It's not something that we know. But if you just extrapolate somewhat wildly to these very high energies, that seems plausible. And of course, in between here, you have the electroweak interaction, where you, in the U1 here, mixes the photon and the Z boson. So it behaves a little bit differently, but you see that the general trends are the same. So you have the electroweak there. Now, if you want to understand why this happens, it has to do with how the charge modifies the vacuum around it. So you saw the vacuum on the first slide, but if you think of a electromagnetic charge, a QED charge, it polarizes the vacuum in a way that it attracts positive charges if it's negative, and then the negative charges are further out. So the vacuum screens this negative charge, which means that in a closed closer you get to the actual charge, and so the strength increases. With the QCD, or the color interaction, it's the other way around. If you're far away, you see this huge explosion of color. And the reason for this is that the carriers of the force themselves carry color, which means that this color just multiplies. And if you had an isolated color charge, it would become completely uncontrollable. There would be color everywhere. And so you cannot have an isolated charge, because this color explosion would make everything collapse. So at large distances, the strong interaction is very strong. But on the other hand, at short distances, if you go inside this cloud of color, the color charge becomes this color charge of the strong interaction becomes quite comparable to the other interactions. What is the solution to this avalanche of color? Well, the solution is that color can never exist as a single charge in nature. You always have systems where the color cancels. And the simplest such system is just having two color charges which neutralize each other. And here you see what happens in such a system. So in terms of the force, you're probably familiar with electromagnetism, and you know that the force drops as 1/r², and you have a field pattern looking like this between a plus and a minus charge. Now, the strong force has a component which doesn't do that. So if you look at the lines which connect the charges, they essentially look like a tube. And you see that the force, maybe it's not so easy to see, but at least there's a hint of it here, that the force doesn't change with distance. No matter where you look, the force remains the same. So there is a Coulomb-like component to the strong interaction. But if you look at the potential then, you see that the further away you go, the larger the radius is, you have a contribution from this linear part, and you have a contribution from the Coulomb-like part, and so you see something which looks like this. And in this potential energy, I mean, the separation, when you separate these charges, that's where you store all the energy or the mass of these particles. But if you go far enough, then so you start with two such charges, you stretch this string, at some point they will break. And because you have enough energy stored to create two new of these quarks. And instead of having one such entity or meson with two quarks, you get two. So there is a limit on how much energy you can store, or how much distance you can separate them. And this is about 1 femtometer or 1 Fermi. So this is very nice, and such particles actually exist, particles consisting of a quark and an anti-quark with a color and anti-color. But the building blocks of matter consist of 3 quarks. So protons and neutrons, which form the atomic nucleus, have 3 quarks, and there it's a little bit different. So here the quarks don't attract each other based on color and anticolor, but instead they try to neutralize the color by bringing red, green, and blue together. Because red, green, and blue together will, again, give you no color. And the anti-version of these colors work the same way. However, so we understand this, but what we don't really understand is how such a proton or a neutron looks like inside. And consider, we know that if we have a charge and then it gets surrounded by this cloud of virtual particles, one very convenient way of thinking of what a proton could look like is that you would have three such particles enveloped in their clouds of color, and together they would make the proton. These constituent quarks, we can use them for calculations, and this works quite well. Each such quark is very heavy, together with its cloud, about 300 MeV, so about a third of the proton mass. On the other hand, you could also consider these very light quarks with this strong gluon field in between them. Then these quarks are called current quarks. And then you have these light quarks with sort of a shared cloud. And if you think about it this way, this is a model calculation where you see the quark mass as function of how fast it moves. So a fast-moving quark will behave more like this. It will sort of shed its cloud and move in a common field, whereas a slow quark will tend to look more like this, where you have your quark, each quark in its own cloud. So both of these types of calculations can be used for understanding various aspects of protons and neutrons. But although they are some level understandable, there is one proton, and we need to really figure out what it truly looks like. So if we really want to know, not based on just model or a specific calculation, we really need to measure the distribution of these gluons inside the proton. Only then will we really understand how the strong interaction truly works. So we have sort of the building blocks, but new experimental tools to take a snapshot of the interior of the proton, and by extension, interior of atomic nuclei, where there are many protons and neutrons, how this gluon field, which is responsible for 99% of the mass, truly works, is still a little bit beyond our insight at the moment. But soon we will have the tools to do it. So one of the methods for exploring this is electron scattering. So and if you do electron scattering, there is a couple of letters which are very useful to know and remember. So this picture here shows you the three quarks, which are bound together by the strong force. And here you have this electron, which comes in and collides with this poor quark here. And so there are three variables to keep in mind. One is called the q square, and that is the forward momentum transfer from the electron. T is the forward momentum transfer to the proton or quark or whatever object you strike. And in many reactions where you don't produce anything, these two are the same, because if you don't produce anything, then the momentum transfer from this guy is the same as the momentum transfer to that guy. However, if you produce things in the reaction, this no longer has to be true. The third variable, which is interesting to keep in mind, is x. And x is essentially the momentum of this particle or quark or gluon or whatever you happen to strike with respect to the proton. So if you think that the proton is moving fast into the right, then the momentum fraction of this particular quark will be the momentum of this quark divided by the momentum of the proton. So this way we don't have to talk about the specific momentum, but it's just relative to the proton. So whenever you see x, that is a momentum, but normalized to the whole proton. And you can see that x is inversely proportional to the energy of the photon. So in order to reach small quark momenta, you need to have very high energies. which may seem counterintuitive, but that's how it works. So now, equipped with this vocabulary, we can look a little bit more specifically at the strong interaction. So this is a measurement of the strength of the interaction as function of this variable Q. And Q is the size of the probe. So it tells you how powerful your microscope is, right? If your microscope is sort of blurry, you don't see very much. If Q is 1 here, you sort of just have a fuzzy image of the proton. If your Q is 100, then you have a very, very sharp image of the protons. So you resolve it in great detail. And that means that but if you resolve it in great detail, it means that you're sensitive to the short distances. And you remember at short distances, the strength was small. If you resolve it poorly, you're sensitive to the long distances, and you see that this force is strong. So if you want to make a perturbative calculation, you typically make an expansion in this parameter here, this coupling, which reflects the strength. And that such a perturbative expansion makes a lot of sense if the coupling here is small, because it means that at some point the terms which you sum up over will no longer contribute in a significant manner. But when this strength is large, such a perturbative approach doesn't work, because every term contributes about the same, and there's an infinite amount of them. So which one do you pick? So this means that when you look at high energies, it's fairly straightforward to calculate these strong interactions. But when you try to understand why quarks bind into a hadron, it becomes very difficult, because then this method no longer works. There are some other methods like lattice QCD where people try to numerically solve this, but it's then complicated in other ways. So, but if we want to understand experimentally how the proton looks like, we need a trick, because the proton size is 1, so we're roughly here, and this is where the force is strong. So the trick is called factorization. And that means that if we have a proton here, I mean, forget about the details for now. So this is your proton. It's coming in here. It's going there. It has some momentum. Remember, T was the momentum transfer. And we scattered an electron of one of the quarks inside it. And in the scattering, you produce some particle. It could be a photon. It could be a meson. It could be whatever. And then this quark goes back, and the proton continues on its way. We have disturbed the proton a little bit, but the proton went back to being a proton. But this entire process can then be written down as a product of two parts. One part, which has to do with this point-like small-scale scattering on the quark, the high-energy part, and one which has to do with the soft interactions inside the proton as it is rearranging itself following this interaction. And this part is straightforward to calculate. And so we have the measured value. We can calculate this part, and then we extract a parameterization of this soft interaction, which is then the one which carries the information about the proton structure. So this is the trick. So we can measure the proton structure through a high energy scattering by employing this factorization. The other trick is called universality, and that is once we measure a process, and it tells us something about the proton structure, which we parameterize with some function, which called structure functions, because it tells you something about the structure. We hope that that parameterization will not depend on the process. It should only depend on the structure of the proton. So it's important to demonstrate that these structure functions are truly universal, And a typical example here is the deep inelastic scattering and the Nadel-Turonski processes. Here you see your proton coming in, and here you see an electron being scattered. It hits one of the quarks with a virtual photon, and the quark continues here. If you flip this diagram over, you can see that it's essentially the same as having two of these protons or baryons, having two quarks annihilate, produce a photon, and produce two leptons. So because these processes are very similar in nature, although this involves electron scattering and this involves collision between two hadrons, you should be able to probe the same structure. And people have shown that this happens, so universality and factorization are the keys. So if you now know all these things, you know how you deal with the fact that the strong interaction is so strong, what do you learn? Well, this is perhaps the simplest measurement you could do, at least the most straightforward measurement you could do, and that is to measure the momentum distribution of these particles. So you randomly hit the particle inside the proton and ask, which probability is it that I hit a particular quark with a certain momentum at a given time? And so here you see these distributions. It may be a little bit hard to read, but there are different flavors. So you have the up quarks and the down quarks. This is on the protons, so you have twice as many up quarks and the down quarks. And but there is also a probability that you will find one quark which carries a very large fraction of the proton momentum. And there is a probability that you will find a quark which carries almost no momentum at all. So these are the distributions for the up and down quarks. What is interesting, though, is that you suddenly see, when you go to very low momenta, that there is a chance that you pick up a strange quark. And you remember there was no strange quark in the proton. So what you start seeing in this region are quarks which pop out of the vacuum. In the vacuum you saw in the beginning, you can just have a quark-antiquark pair pop out from the vacuum, and you can happen to hit it with your electron. But most importantly, you see here the gluons. So you have very few gluons with large momentum, but at low momentum, you have a very large number of gluons. And these are the force carriers, which then keeps the proton together. Now, you have very many of them. Exactly how many depends a little bit how you do it. For those of you who are expert, this is a next to leading order fit. This is a next to leading order fit. This means that you have kept more terms. And you see that the gluon distribution has slightly different shape here at the very lowest x. This does not necessarily reflect how many gluons there are, but just the way this fitting procedure is done. We'll come back a little bit to that. This uses a certain set of equations for this extraction, which may not be completely valid in this region. But the global trend that you have, this rise in the low momentum gluons, is a general feature. Now, so this was the momentum distribution. But if you want to know how these gluons are distributed in space, you have to use another trick. So the easiest way to measure spatial distribution is called form factors. So form factors essentially are related to a Fourier transform. In this case, between distance and momentum. So if you have something which is point-like, so a particle which is really a point-like particle, the Fourier transform of that is just a constant. If you have a proton, which is sort of a little bit fuzzy charge distribution, which is an almost black disk with sort of fuzzy edges, will give And the trick here is that when you measure a cross-section for something which is not a point, you say, well, let's write this measurement as a product of scattering on a point particle times something. And this something is the form factor. And then you can do the Fourier transform and have your form factor in Q. Here is the momentum. Instead, you will get the distribution as a spatial coordinate. So when you scatter on something like this, you can say this is a scattering on a point particle times a form factor, and from this form factor, you can then extract this charge distribution. So traditionally, people have measured form factors to understand the spatial distribution inside a particle, and they have measured momentum distributions to understand the momentum. But recently, there are ways of combining the two. And this is the really interesting part. So if you really want to understand what your proton looks like, you can combine the measurement, which tells you what it looks like spatially in the transverse plane, with the measurement which tells you what the momentum is of the particle which you hit. So you may hit the particle here, and it may have a certain momentum. And if you combine these two, you get something which is called a generalized parton distribution. And this is this 3D image of the proton. And for those of you who are interested in the details, I can just mention that that's a little bit of a simplification, because in reality, the elastic form factors are an integral over x, whereas the momentum distributions, so parton distribution functions, are in the limit of zero momentum transfer. But everything in between is also covered by these generalized parton distributions. And that involves correlations between particles and a lot of other things. But broadly speaking, if you keep in mind just this idea, that these distributions allow you to form this three-dimensional image of the proton, I think that that's already very important, because this is something we can measure these days. And so here is just an example. Now, this is not a measured distribution, but this is if you look along the direction of motion. So you can see here B is the impact parameter, or the distance from the center. And so you can see B in X and B in Y. And you can see how this changes for a up quark polarized in this direction. Now, there is also another type of distribution, which is related to this one, which does the same trick, only not in X and Y space, but in momentum space. So instead of saying that there is a certain probability of finding a quark in a certain location, it tells you there is a certain probability of finding a quark with a certain momentum. And this is not the longitudinal momentum, but this is the transverse momentum. So this is essentially a three-dimensional picture in momentum. And equipped with these two, you can now have a fairly good idea of what is going on with the quarks. And an interesting thing is that I will talk a little bit about this spin and the orbital motion, but both these distributions can potentially give you access to that. They are experimentally measured in slightly different ways, but they are from the same family of distributions. So if you want to see what the projections look like for the Electron-Ion Collider, so this is what would actually be measured, you can see, for instance, here, if you produce a J psi, and J psi is a charm plus anti-charm quark, and this J psi is then sensitive to the gluons because there is no charm in the proton. but some people think there may be a little bit of charm in the proton, but this is very unlikely to find a charm quark. So if your photon produces a charm anti-charm pair, it means that there was an interaction, and you see these two gluons which couple to something, and that is sensitive to the distribution of the field inside. And then you can see how your distribution of gluons or distribution of the field varies with momentum and distance. So you have these different slices here. And this is sort of a similar way of thinking, but in this TMD or momentum picture, this is another function which is called the Sievers function. And then you can see how that changes as function of x. And in this case, quark transverse momentum. And the relative transverse momenta are lower than the GeV because GeV is sort of the proton size, right? So the intrinsic momentum of the quark inside the proton will be less than that. So I mentioned the spin. And the spin is also very interesting because naively we would think, well, we know that the spin of a proton is 1/2. But the question is, how does it become 1/2? And naively, you would think that there are 3 quarks, and each quark also has spin 1/2. So if the quarks are not moving, they are in an S state, 2 will be pointing one way, 1 will be pointing one way, and the difference is 1/2. And that's a very good idea, except it's not true. So why is it not true? Well, because the interior of the proton looks much more complicated. I mean, inside this proton, you have this constantly forming and disappearing pairs of virtual particles, and you have all the gluons. And while they are not permanent in a sense, while they are there, they do things. And if you want to write down what this 1/2 truly consists of, you will have a contribution from the polarization of the quark, and the polarization of the quarks means this. So some quarks will be pointing one way and some the other way. But you will also have a contribution from the orbital motion of the quarks. And we think now that the orbital motion of the quarks is not negligible. So this idea that they are just sitting there in an S state is not entirely correct. But then we have the gluons, and the gluons also have a polarization and an orbital part. There are ways of measuring these. The polarization of the quark is perhaps the most straightforward one. A lot of people have been working on the gluon polarization, in particular at RHIC at Brookhaven as a big spin program to measure this particular distribution. But the orbital motion is very, very hard to reach. And the reason for this is that you have this very fast moving particle, and then you want to look at the very tiny transverse motion. And typically in the framework where you try to look at things like delta G or delta sigma, you neglect this transverse motion. So really you need something like the GPD or TMD, this 3-dimensional picture, to form a relationship which gives you access to this orbital motion. Only then will you have all the different components in this decomposition. And now this is, you can write down such an equation. This is the G-sum rule, and you see that there are different names for these structure functions, the GPDH and the GPDE. But the problem is, of course, measuring this, because you have to measure it everywhere, and that's a little bit tricky. So it's a big program to try to do this. There may be other ways, but these measurements, ongoing measurements of delta G, but also the future measurements of this 3D structure are both very important to truly understand how this decomposition works. Of what is these terms are slightly rearranged here. So this is sums up the recent results from the Brookhaven spin program, and so here you have the contribution from the quark polarization and the gluons, which is this one, and if we then forget about the orbital motion of both the quarks and the gluons, so here you have a function of momentum, and here you have a quantity which you integrate over. So this is essentially the gluon polarization, but what you really want is the integral of this thing. And you see that at the moment the problem is that Brookhaven does a good job up here, but doesn't quite reach the lowest x. So the hope is that in this aspect as well, the EIC will be helpful, because if you reduce the uncertainties in the lower x region here, so for the low momentum gluons, you will be able to shrink the error bars significantly. So here you see delta sigma plotted versus delta G, and this is the current understanding where you have a rather large uncertainty. And so the hope is that by reducing this uncertainty, you reduce these uncertainties as well. But these terms have to be measured in a different way. So you see that future measurements can greatly understand not only help us understand not only the distribution of the field inside the proton, but also how the spin comes about and which pieces contribute to the spin. Now, if you just look at the proton, it actually looks very different. If you sort of think of it as a slice at different momenta, it looks very different depending on which momentum you're looking at. So in this case, here is your momentum scale. So this is large momentum and this is small momentum. And there are two frames. This is the rest frame. So this is the frame where the proton is standing still. This is what I call the detector frame. So if you have your collider, your proton is moving by at a very high velocity. And so this is what it looks like in the detector frame. Now, if you want to be more stringent, you would probably call this the infinite momentum frame, but that's sort of just a detail. But what is interesting is that in this picture, your proton or nucleus is compressed. So your quarks will be lying in a disk. But then you have some interactions between them. So you have some gluons. You remember, as you go to low momenta, this number of gluons, this is now in not a logarithmic scale, but a linear scale, this number of gluons greatly increases. So, and it increases because the gluons split. You remember the very first picture when the one color charge splitting led to many color charges, and you got this very big increase or this explosion of color. So you have a lot of gluons by splitting, but these gluons are a little bit slower. So when your proton is moving at high velocity, it looks a little bit like a comet, right? It has this tail of low momentum gluons behind it. So, but the density of these gluons becomes very large, and eventually they sometimes meet up and start recombining. So if you look sort of at the moving proton, it will look like this. If you, on the other hand, look at the proton that stands still, you will start with your 3 quarks or your 3 charges, but then you sum up over all these, and you see that there's more and more of them until you really get this color soup when you get to the very lowest momentum. So no matter how you look at your proton, it looks very, very different depending on which slice in momentum you pick. And so if you pick something around 1/3, you have the 3 valence quark region. If you pick something in the middle, you have the C quarks, so these virtual quark-anti-quark pairs which pop up from Heisenberg's uncertainty relation in the vacuum. And then at the end, you just have a lot of gluons with just essentially QCD radiation, right? And you can understand this also in a slightly different way. So if we now take this and combine it with the Q, which is the size of the probe or the strength of your microscope, If you look at large Q, which means small scale, so it's not a quark that gets smaller, but it's a microscope that gets more powerful, you see that you will have a few quarks or charges which are tiny. Now, if you then move to a lower scale, so larger probe, you will still see about the same amount of charges, but the charges will now appear large. If you go, on the other hand, to low momenta, the number of charges will increase. So if you went up from here, there is no picture, but you would have a larger number of charges, but which would be of this size. And here you would have an even larger number of charges, but if they were up here, they would again be small. So at some point, you will have color everywhere, and this is called saturation of color or gluons. But this requires you to have relatively large gluons, or having a lot of them, or the appropriate combination of the two. And once that happens, you enter a state which is called a color glass condensate, which has some features reminiscent of what you see in solid state physics. But the key here is that you can do it in two ways. You can increase the number of gluons, or you can increase their size. Of course, at some point, your microscope will be so poor that you can't see anything, so you need some resolution, right? So you can't go this way too far, but you have to find a good combination of these other parameters. And so if you want to see what happens in this particular state, we either need very high energy, sorry, or a lot of gluons. And getting the high energy is very difficult. You need to build a very big machine to collide these particles. But there is one other trick for increasing the number of gluons. And that is, you don't take one proton, but you take many protons. And you say, how do you take many protons? Well, you take a nucleus. A nucleus, a heavy nucleus, contains 200 nucleons. So this gives you a very nice boost. And the trick here is, depending on which frame you're looking at, but if you look at in the detector frame, or the frame where this nucleus is moving fast, it essentially is just a thin pancake. If you think of it as moving slower, at low x, the photon itself is very large. So it becomes larger than the nucleus. Either way, it interacts with all the gluons in its path. So it doesn't care that it's in one proton or the other proton. So by having a nucleus, you can enhance this effect. And essentially, by having this larger radius. And this is how we hope to look at this high gluon density in the future Electron-Ion Collider. That's also one of the reasons why the nuclei are important to be able to use. There are some tricks to further enhance this, but this is sort of the principle that you can sum up gluons over larger distances than just a proton. So talking about ions, if we want to learn what can we do with ions, there's sort of three areas where an electron-ion collider can help us reach some new insights using ions. Well, there could be a lot of things. This is just a few examples. But one is neutron structure. Proton beams are relatively easy to make. It's tricky to build a collider, but it's much trickier to build a collider using neutrons, because it's very difficult to accelerate neutrons. And so typically, what you do is that you take a light nucleus, which like a deuteron or a helium-3, which contains a neutron, and say that this neutron is your target. And then you make sure that you scatter on the neutron. The problem is that you have all kinds of nuclear effects. So you need to understand your few body physics very well to make sure that you really do the interaction with the neutron, but don't have additional interactions. And there are some tricks for doing that. Another very interesting area is when you put these neutrons together into a nucleus, so neutrons and protons, they are no longer the same as if they were free. And this is not just a trivial effect that their mass changes slightly because of the binding energy. You really see very fundamental differences in their behavior. So the question is, when you put the nucleons into a nucleus, what does really happen? And this will tell us also a little bit about why truly nuclei are formed. I mean, there are very good effective descriptions of nuclei, which are perfect for calculating a lot of quantities. But if you want to have a more fundamental understanding why protons and neutrons bind into nuclei, have sort of QCD description of how a nucleon changes in the medium is very important. And the third is what you saw before, what happens when we have these coherent interactions. So essentially something which looks like gluon saturation, and their nuclei are an essential tool for reaching that regime. So let me just give you a few short examples. I will not go into details, but I think this is a very nice trick, because you can actually have a free neutron target. And so this is deuterium. In this case, you have a deuteron coming in here, and here is your electron. It hits the, well, it could be any of the two, but you're probably interested in neutrons. So it hits the neutron, and stuff comes out. And the proton continues as a spectator. It didn't take part in the interaction. But how do you ensure that it doesn't take part in the interaction? Well, you can measure the momentum transfer, or specifically the mass squared minus t here, but that's a detail. And it turns out that there is a minimum momentum transfer, which makes this sort of kinematically acceptable. And however, you can extrapolate to what is called the pole, but it's essentially when this is 0. This is not physically reachable because it would break your kinematic equations. But if you measure with high precision, you can easily extrapolate to the pole. And this is very interesting because at the pole, you by definition have a free neutron. So even though you don't have a free neutron inside the deuteron, by extrapolating to the pole, you measure whatever you measure. There is an example here with F2, which is essentially the probability of the cross section, but it could be any quantity. So you can measure it as if the neutron was free, assuming that you can detect the spectator with great precision. So this is something you can do in a collider, which is a very nice feature. In terms of medium modifications, well, I will not go into details, but let me just show you this. This is because this is very interesting, and this we can already see in data, say at JLab. So I told you that x was the momentum fraction that this quark had. And by definition, x could not be greater than 1, because if x is 1, it means that it has the whole momentum of the proton. However, if you scatter off of nuclei, of quarks inside nuclei, you see these plateaus. So here you see a plateau where x is greater than 1. So what does that mean? How can the quark have more momentum than the proton? Well, there must have been more than one proton participating. And so this traditional model of a nucleus, you probably all have heard about the shell model with neutrons and protons moving in various orbits, is not entirely true. There is a strong component where protons and neutrons in particular like to stay close together in a very high momentum state. And when you kick one out, the other goes in exactly the opposite direction with a large momentum. And this is not just at the level of the nucleons, because if you hit one quark, this quark can easily pick up the momentum from all the quarks in the other nucleon. And this is why you can reach x of 2. Or if you have a 3-nucleon correlation, even 3. So this is a slightly different way of thinking about what happens in a nucleus. But these are existing data. And very interestingly, this correlates very strongly with something called the EMC effect. I will not go into details of that, but this essentially tells you that the probability of scattering of a quark inside a proton inside a nucleus has a different shape than the scattering of a quark in a free proton. But the correlation between these two is very telling. And there are two different pictures here you can have. One is that you have correlations between free protons and free neutrons, or you can have modifications of the properties of these nucleons inside the nucleus. And probably you have a little bit of both. But this tells you that the binding inside the nucleus is not just simply a matter of some average field. A lot of interesting thing happens to the constituent particles inside the nucleus. But and hopefully we can learn more about that also at an EIC. And I mentioned already the coherence and gluon saturation. That's another key measurement where the nucleus is a tool for studying the QCD radiation. And finally, I wanted to show you that one can look at energy loss and PT broadening in hot nuclear matter, but one can also look at in cold nuclear matter. And if you know the energy of your incoming photon, now the photon will interact at some depth. It does not necessarily interact at the surface, but if you know the energy of your incoming photon, the size of your nucleus, or maybe better still, the path length, which you can do by forward tagging of the remnants, you can know whether the hadron is formed inside or outside, and you can know how far your colored charge propagated in the cold nuclear matter. And this is in fact also linked to saturation in somewhat indirect way, but this is another measurement with nuclei which you can do. And I will finish off this section by talking about diffraction. So in optics, and I mentioned that already in talking about the form factor, but if you scatter light off of a sphere with sort of either hard edges or semi-soft edges, which is more like the nucleus, you will have some kind of diffractive pattern like this. And this diffractive pattern tells you a lot about this object, in particular its size here. So this is in optics, but it's very similar when you scatter off of a nucleus. So in this case, you see an example of electron scattering producing a meson off of a nucleus. And this is what you measure. In this case, here you have the momentum transfer as your variable, just as in the form factor discussion, which you may remember. And you have two components, one which is so-called incoherent. And this means that you really didn't scatter off the whole nucleus. You just hit one of the protons or neutrons inside it, and that sort of just gives you a somewhat flattish distribution, just as you would get in a proton. But you can also have the scattering coherently from the whole nucleus, in which case you get this diffractive pattern. And if you take then the Fourier transform of this diffractive pattern, you can get back the shape of your nuclear potential. And so it's very similar in concept to the scattering on the proton, but it's trickier because you have to understand how these minima are distributed. And you see there are very few events here because this is a logarithmic scale compared with here. So and you also have this very large background. So let me do this in opposite order. So the question is how many of these minima do you need? Well, it depends. So because this is a Fourier transform, large momentum transfer corresponds to short distances and vice versa. So if you only include a little bit of this distribution, you will do your edges well. So you see small t, so this will be the opposite here. Right? So small t means large b. So if you only include the beginning, you will get the edges right, but you see in the middle, it doesn't look right. So this is an attempt to reconstruct whatever you put in, and you see that it doesn't do a good job in the middle. If you go further out, you see that also the middle looks good. So you probably need at least 3 of these dips to make a good measurement of the interior of the nucleus. What I try to show here is that this is, by the way, also interesting in the context of this saturation, because you remember the number of gluons and their size depended on your probe, and some of these mesons are simply bigger. So if you take a J psi, which has a charm anti-charm quark, it's naturally very tiny, and that's driven by the mass of the charm quarks. So it's if you want to be a little bit more accurate for such a heavy particle, you would say that the scale is not 1 over q, but 1 over m plus q, and the mass here is large. So it means that you have a small object, so you don't really see this saturation very easily. Whereas if you produce a phi meson, which naturally is rather large, it will be much more sensitive to the saturation. It sees much bigger gluons. So by comparing, say, a phi to a J psi in such a diffractive measurement, you can learn about this saturation. Now, you can also do the phi at the higher q square, because you remember that makes our microscope more powerful, so we can sort of zoom in on a smaller distance. So, but it's technically difficult. So we need very, very good detection to distinguish between this signal, which is the diffractive pattern from the nucleus, and the scattering on a single nucleon inside it. In fact, we need something like 99% efficiency in rejecting this part. And so what you need is a very sophisticated detection for nuclear fragments, because we need to make sure that we don't miss one, right? If there is any fragment, it means that this was not the right process. So I could just briefly show you, without going into too much details, that if you build such a detector, you have some central detector here, but in reality, you have something like a 100-meter-long stretch over which you do the detection of all the outgoing particles, because in an EIC, most of the particles will go very, very near the beam. So when you think about your detector, don't forget that the big part is here, but the long part is here. And we need both of them to be able to do this type of measurements. And if you want to do this stuff, you need to integrate it very, very closely with the accelerator. Because if you build a spectrometer, which essentially this is a 50-meter-long spectrometer, the way you sort of shape the functionality of the spectrometer has to be compatible, which you may include focusing or changing the dispersion or whatever, must be compatible with the way that the accelerator operates. So many of these measurements are extremely interesting, but also require a lot of preparation. So let me say now a little bit more about the actual project. So that was a very lengthy introduction to why we do these things, and maybe hopefully gave you some ideas of measurements that could come up. There is, of course, a lot of other measurements you could do, which are also very interesting. But in terms of the facilities, so you remember that this is, if you just look at this plot, when you have this momentum distribution or X distribution, x here is q squared divided by the total energy times inelasticity, which we can neglect for now. But essentially, the higher the energy, the lower the x. So if you want to look at the low x, or low momentum region, so the virtual C or the gluon saturation, you need high energy, something like an electron-ion collider. If you want to look at the high momenta, you need something like the JLab 12GV program. So essentially, these two are very complementary in what they do. Together, they cover the whole range in momentum. And this facility already exists, but this is the future facility where perhaps a lot of new interesting discoveries will come. And let me just show you. So this was I think Chao Chun mentioned that in the introduction, in the next long-range plan, the EIC features highly as the recommendation for the next facility. And this is the EIC white paper, from which I stole the title of this talk, by the way. So the glue that binds us all, right? These are to understand the gluon field in the proton and in nuclei. And these are the two proposed sites. So Brookhaven would convert the relativistic heavy-ion collider. JLab would add another ring to its existing fixed target facility. Now, what should be mentioned, and maybe some of you know a little bit about this, is that there was an electron-proton collider called HERA some time ago. And people learned a lot about this type of physics from HERA. But the EIC is not just another HERA. There are several very important differences. And the energies of the EIC are lower, but the luminosity, so the ability to look at rare processes, will be much higher. The HERA did not have any ions other than the proton, which means that anything related to what we discussed about ions could not be measured. HERA also did not have any polarization, which means that many of these three-dimensional distributions could not be measured because they require polarization of your target. And the HERA detectors, well, they're optimized for searches of leptoquarks, which were in fashion at the time. Turned out that they didn't discover any leptoquarks, but the legacy stayed, and they couldn't do many measurements because of the limitations they built into their detectors from the beginning. So hopefully the EIC will not make this mistake and will be able to discover everything that it potentially can without prejudging it too much. So this is the current site at Brookhaven, and you probably have heard of the Phoenix and star detectors. And the idea here is that eventually in the RHIC machine, this location will become the EIC as Phoenix, and maybe another detector would be built here. At JLab, there is an electron accelerator, a 0.9-mile racetrack, with 3 holes here and another hole here. And the idea would be that this would be used as an injector to a future collider complex. Now, the energies at JLab are significantly lower, which is not an advantage. The advantage here is that you have this figure 8 shape, which allows you to have polarization of deuterium, or essentially polarized neutrons, which could be interesting for some measurements. Let me just show you briefly the detector concepts which go with it. So I mentioned the S-Phoenix upgrade. The S-Phoenix detector is now being built for the next phase of the RHIC program at Brookhaven. But there is ongoing effort to then transform it into the first EIC detector. And in principle, this could be used at any site. So the detector which is being built is a nice detector, and it can be used regardless of accelerator location. But most likely it will, of course, be Brookhaven. So this is a picture from a simulation. This is sort of more technical drawing, so you can see that it's not just Lego-like blocks, but there are more detailed studies being done on how the various subsystems are distributed and so on and so forth. There is another concept for a detector at Brookhaven called the Beast. It looks somewhat similar. You have calorimeters all around it. You have particle identification detectors on the sides. I particularly highlighted the detectors on which we are doing the R&D, and the detector which specifically is being developed here at GSU is the one for this part. As you can see, broadly speaking, these detectors start looking somewhat similar. Originally, they all differed quite a lot, but both after 2016, this detector changed to look much more like the others, and I think that Phoenix has also evolved a little bit. So if you look at all these detectors, this is a sort of a top view of the JLab detector. They differ in some details, but they are converging, which is a very good sign because it shows that people see that the physics requirements sort of push your ideas into a certain direction. And here also you see the PID detectors, which I mentioned earlier. So there is this R&D program which is already ongoing and which will expand as the construction nears. Let me just give you a few examples for particle identification. So the challenges are twofold. There are electrons which look like negative pions, and there are pions which look like kaons, and there are both varieties. So there are pi pluses and pi minuses and k pluses and k minuses. And if you're not able to distinguish between them, you don't know which quarks participated in your interaction. You still can learn something, but you can learn more if you can actually know which quark was there and which quark was struck. So it's important to cover as much as possible of your reaction products with this particle identification capability. And here you can see sort of a very broad distribution, which includes all kinds of processes. So it may look different if you pick a specific one, but as function of angle, which is colorability here. But this is essentially one side of the detector, this is another side. This is very squeezed. So this part in the middle here corresponds to this very large piece of the detector, whereas, say, this part from 4 to 8 corresponds to this, essentially the region along the beam pipe. So this is sort of a scale which you have to get used to, but you need slightly different types of detectors in the different parts to cover all the particles. And so there are different technologies which are preferential. On this side, this modular aerogel rich is ideal because it's compact, has good performance, which exactly matches the requirements of the EIC. In the middle, you can have a Dirk detector. On this end cap, you can have a large gas rich, maybe in combination with an M rich. And that way you can cover everything from high momentum to low momentum. So I just wanted to show you a principle for those of you who are not familiar with Cherenkov radiation. What Cherenkov radiation is essentially a particle traveling faster than light in the medium, which is allowed, right? It's very similar to when a particle travels faster than sound in the atmosphere. Only this is and then you have a shock wave coming out, and the angle of this wave will then depend on the velocity. So this is very similar, only in the electromagnetic field. And the Cherenkov radiation is mainly blue. And this is just a picture of Cherenkov radiation, because if you put a lot of decaying nuclei in water, you will have electrons, beta decay. And these electrons go faster than light in water, and so they radiate nicely. And in a reactor, you have a lot of these decays. So reactors are sort of shiny blue, and that's because of the Cherenkov radiation. However, if you now can measure this angle, you can also tell something about the velocity of the particle. And if you know the momentum and the velocity, then you know which particle it is. So let me just show you briefly how a couple of these detectors work. So DIRC was this very long, narrow bar. And so you have this Cherenkov process, you create the photons, but then you have this bar with a high index of refraction, and the photons are reflected internally, and the image is projected on a screen, and then you have your photosensors, and you measure the ring segments on the screen. So you need to have a very, very precisely manufactured bar, because the surface has to be very even, and the surfaces have to be very parallel for this to make sense, because you're measuring very, very tiny changes in angle. What you do is then you get some kind of fish-like pattern like that, and it looks a little bit strange. But if you combine the X and Y information with a precise timing, you can get a very, very good performance. And the R&D we are doing is quite impressive, because the previous existing DIRC detector, which was at Babar at SLAC, could do a 3 sigma separation for pions and kaon at 4 GeV. We think we can build a detector which can do 4 sigma separation at 6 GeV. It's quite a significant improvement. Sorry. And the MRHIC is a very, very nice detector idea, because it's very compact, not as compact as the DIRC, but it has a higher momentum reach. So it's very compact for its performance. It's a big improvement compared with the previous generation of detectors of this kind, which were proximity focusing detectors. There you get a large ring, and here you get a small ring, but with the focusing lens, this ring is very sharp. Which means that if you have a sensor with small pixels, so focusing plus small pixels allows you to resolve this ring very nicely. And furthermore, because of the lens centers the ring, you need a smaller sensor area, because if your particle doesn't hit in the center, the lens corrects the image. So it's not just smaller and sharper, but it's also centered. And the momentum reach is exactly the one we need. And there has been, the results have been published, and here you see some view of the prototype. This is S-Phoenix, where you see the MRHIC will be used probably here and there. So very, very ubiquitous detector. Oh, almost. Then there's also this big gas rich, which you're working on. I think I can skip that part. So I try to give you an overview of the physics opportunities which we will have at the future Electron-Ion Collider, and say a little bit about the implementation. Of course, it's a very broad topic, so I sort of just scratched the surface, but I hope at least it got you interested in what could come. So thank you very much.
I have to claim that you probably had the record of the longest introduction of physics, but you are doing much better than I could ever dream of. Excellent. Let's have a few minutes to entertain any questions you may have.
Do you have when the timeline will be to make a decision between Jefferson and Brookhaven?
So I think that, well, I don't have the answer, but I think it's a question of a few years, because I think both labs will present the project, and then, so CD0 hasn't happened yet, right? And then after they both present the projects will be evaluated, and a site will be selected. But what is important is that I think there's a lot of work on the sort of general physics and also on the detector technologies, which is really independent of the location of the accelerator. So in some sense, you can say that the program is already moving ahead, regardless of the site.
I have a conceptual problem.
That sounds interesting.
Spin is an intrinsic property of particles. Orbital angular momentum is not.
Yes.
It seems to me that if part of the proton spin comes from orbital angular momentum, it should be possible to